Today we will be continuing with the application of inductive effect. So in our previous video we have discussed about one of the application of inductive effect, that was reactivity of alkyl halide. Today we will be discussing about the second application, that is acidic strength of acids. Okay, so relative strength. This is the second point, relative strength of acids. So inductive effect can also explain which acids are going to be stronger, okay, and which acids are going to be weaker than the other acids. So let's take an example. Suppose you have, say, acetic acid, CS3, COOH. Now whenever this dissociates, it gives us CS3, COO minus plus H plus ion. Now let's take another acid, that is a fluoroacetic acid, CS2, COOH. So whenever this dissociates, it gives us CS3, COO minus plus H plus. Now here we have fluoro. So CS2, here we have Cl. Okay? So the relative strength of acid, the strength of acid is determined by H plus ion that can be generated. More the H plus ion generated, more will be acidic strength. So for this more H plus ion to be generated, this conjugate base, this is known as what? Conjugate base. It depends upon the stability of the conjugate base. If the conjugate base is more stable, that acid is going to be more acidic. So this is the conjugate base of fluoroacetic acid. So let's compare the stability of these two conjugate bases of this acetic acid and fluoroacetic acid. So I told you, here you have to remember what? More the stability of the conjugate base of the acid, more will be its acidic strength. So here, let's take this conjugate base of acetic acid first. So in this, we have, say, this negative charge. Now this negative charge, if it can be dispersed over more number of atoms, then that will be more stable. Okay? Now in this case, you can see that this has oxygen, has minus charge. This minus charge influences even this carbon. That means some amount of negative charge is also present over this carbon atom. Now here you can see that you have this CS3 group. This CS3 group is present. So let me make a bond over here. So this CS3 group is present. Now you know CS3 group shows plus I effect. Plus I effect means that its electron will be shifted towards this carbon atom, which implies now there is more negative charge over oxygen as well as this carbon atom. Negative was already there. Now more negative is coming towards this carbon atom because of the plus I effect of CS3 group. That means this conjugate base is not that stable. If it's not stable, that means since it's a reversible reaction, these two will combine to give you back what? Acetic acid, which affects the concentration of H plus ion. That means you will have less amount of H plus ion. Now let's come to the conjugate base of fluoroacetic acid. In case of fluoroacetic acid, this negative charge is also present over this carbon, some amount of it. Now this fluorine, you know fluorine is more electronegative than carbon. This fluorine is more electronegative than carbon. Then now this fluorine will show minus I effect. This will show minus I effect, whereas this was showing plus I effect. Now due to the minus I effect of fluorine, what will happen? Now it will help in dispersing this charge over chlorine atom also. That means it will stabilize this conjugate base. Now I told you, the conjugate, if it is conjugate base, if it is more stable, that will be more, that acid will be more acidic. That means in comparison to these two acids, chloroacetic acid is stronger acid compared to acetic acid. So you can remember this way, whenever you are comparing about acidic strength based on inductive effect, whenever you have minus I effect showing cross, those acids will be more acidic compared to the ones which shows plus I effect. Hope this is clear. Now let's move on to the third application, that is the relative strength of base system. We will be discussing about relative strength of the bases. Just now we discussed about the relative strength of acids. Now we will be discussing about relative strength of bases. Now here say bases are those compounds which will be able to donate its lone pair of electron. So let's compare about say ammonia. This is say ammonia, and say we got CS3 and H2. Now out of these two bases, which one will be stronger? Let's compare, okay? By application of inductive effect. In this case, you can see that nitrogen has lone pair, and over here also nitrogen has lone pair. Now in this case, this lone pair over nitrogen is present, therefore it acts as what? Base. Now whenever you come to this group CS3 and S2, the lone pair is present over nitrogen, and the basic strength will depend upon how easily it can donate its lone pair of electron. Okay, so in this case you have CS3 group will show plus I effect. Plus I effect will enhance the electron density over nitrogen. That means it will make more electron dense over nitrogen. Now therefore this will be willing to always donate its lone pair of electron. Whereas here in case of ammonia, you do not have such plus I effect. Now by application of this plus I effect, we can conclude that the amine containing CS3 group is more basic compared to ammonia. Okay, so you have to remember this example. Or you can also have say, if you have say chlorine group over here. Okay, if you have chlorine group, then obviously this chlorine will show minus I effect. Because of minus I effect, the electron density over nitrogen will be decreased because it will be pulled towards chlorine. Now this will be even less basic than ammonia. Okay, so why? Because this lone pair, now this nitrogen is not willing to donate the electron. Why? Because of the minus I effect of chlorine. Okay, so these are the three main applications of inductive effect. Now let's discuss about the next effect, that is electromagnetic effect. Electromagnetic effect. Electromagnetic effect. Now this electromagnetic effect differs from inductive effect. In what respect? In the respect that here in electromagnetic effect, for a compound to show electromagnetic effect, there has to be presence of double bond and some attacking reagent has to be present. For example, suppose you have this compound, say C double bond O, carbonyl compound. Now there is always a double bond between carbon and oxygen, and it is always like this. But in presence of some nucleophile, say Cn minus, what will happen? Whenever this Cn minus is brought near to this carbonyl compound, then there is transfer of electron. Here this is delta plus, this is delta negative, more electronegative, this is delta positive. Now whenever in presence of attacking reagent, Okay, what will happen? There is a permanent shift of this pi electrons. This will be bonded to this, and this will be shifted this side. That means you will be having CnO minus now. Okay, so there is a permanent. This double bond has broken, and there is a permanent. It's not a permanent. It's a temporary shift. Why temporary shift? Because this shift takes place in presence of this attacking reagent on. Okay, please remember it's a temporary shift. Now, as soon as you remove this attacking reagent, then what will happen? This shift will not take place. So you have to remember what? There is complete transfer of said pair of electrons of multiple bond to one of the bonded atoms under the influence of an attacking reagent. So this effect is known as what? Electromagnetic effect. Now, like you have the inductive effect, whenever there is some alkyl group attached to it, say CH3, you have CH3, CH, double bond CH3. Now what will happen is CH3 will show plus I effect, and because of this will be shifted this side. Now, here it is known as what? It is known as, because of plus I effect, the electron is shifted this side, and this is known as plus E effect, plus electromagnetic effect. Now, whenever you have electronegative atom attached to this double bond, then what will happen? This will be showing minus I effect. Chlorine is more electronegative. Because of that, this will be shifted this side. Now, this is known as what? Minus E effect. Okay? So plus I effect is somewhat like plus I effect, but here there is a complete transfer of electron. Please, complete shift of electron. Now, on page number 12.65, you have the difference between electromagnetic effect and inductive effect. So please go through these differences. And since I have already explained what is electromagnetic effect and inductive effect, your responsibility is to remember these differences. And many of the, if you have listened to this class properly, many of the differences you already know it. Now let's move on to the next effect, that is resonance effect. Resonance. So, resonance is a phenomenon. See, now whenever the actual property, okay, of any compound cannot be explained by any of the structures. Like for example, let's take benzene. The benzene structure could be this, or it could be the double bond here. Again, this is structure 1, this is structure 2. Now, the actual property of benzene cannot be explained all alone by only this structure, neither it can be explained by only this structure. Now, the actual property of benzene lies somewhere in between, and they have concluded what? The actual structure of benzene is this, because this is the actual structure of benzene, which shows that this double bonds, these pi electrons are not fixed in, it's not localized in the benzene ring, they keep on resonating. Now, such structures are known as canonical structure or contributing structure, and this phenomenon is known as what? Resonance. Okay? Now, on page number 12.66, you have the definition for resonance. Please look at it. In cases where more than one structure can be written for a compound, like you could write 2 structures for benzene, yes or no? For a compound, but none of them is able to explain the known properties of the compound completely. The different structures written are known as the resonating or contributing or canonical structures. These structures are resonating or canonical structures, And this phenomenon is known as what? This phenomenon is known as what? Resonance effect, resonance or mesomerism. Hope this is clear. Now you have to remember this, that wherever resonance is possible, that particular compound is highly stable. That compound is highly stable. And here, why benzene is strong? Benzene is stable because resonance takes place. And let me tell you that here you can see in benzene there is double bond, there is single bond. Yes or no? But the actual bond length of carbon, these are carbons, no? Carbon, all carbons. The actual bond length between carbon and carbon atom in benzene is not that of first order, nor that of second order. It lies somewhere in between. Okay, the actual, see, for single bond, the carbon-carbon length should be 1.54 angstrom, and for double bond it should be 1.34 angstrom. For single bond it is 1.54 angstrom. For single bond, and for double bond it is 1.34 angstrom. But the bond length of carbon-carbon in benzene are all equal, and it is what? 1.39 angstrom. Now this shows that the bonds in the carbon-carbon bonds in benzene are neither double bond nor single bond. Okay, and because of this, it means that resonance has taken place. Electrons or electrons are continuously resonating inside the ring, and this gives stability to the aromatic compound. So now let's discuss about resonance effect or mesomeric effect. Likewise, here also you have plus M effect, resonance. This is also known as mesomeric effect. Mesomeric effect. So likewise, as you have in this inductive, you have plus I and minus I. Here also you have what? Plus I and minus I. So let's take an example. Here, suppose you have benzene and some groups are attached to it. Now in this case, oxygen, you know, it has lone pair. Now this lone pair can be shifted inside the ring because of resonance. Okay, and such groups which are donating its electron inside the benzene ring, they are known to show plus R effect or plus M effect. And other groups, like let's compare between say C double bond is present. Now such groups, now here oxygen is more electronegative than carbon, therefore this electron will be shifted up and the electron of the ring will be pulled upwards. That means because of this C double bond O, there is decrease in the electron density in the ring. Now such groups are known to show minus R effect or minus M effect. Okay, so you have to remember, if there is electron donating group inside the ring, then that will show plus R effect, and if there is electron withdrawing group from the ring, then those groups are known to show minus R effect or minus M effect. Now let's discuss about application of resonance. So this application of resonance is very important. Application of resonance. Number one. So number one, we have relative strength of acids. So relative strength of acids. So the same thing can be applied. If the conjugate base is more stable, then that particular acid will be more acidic. So here, let's compare between phenol. This is phenol. You have OH, and let's say alcohol, C2H5OH. Now, when you take dissociate. It dissociates as O minus, and here this will dissociate as C2H5 O minus plus H plus. So the same explanation here. This is the conjugate base of phenol and this is the conjugate base of ethyl alcohol or ethanol. Now the acidic strength will depend upon the stability of the conjugate base. More the stability, more will be its acidic strength. So in this case, in case of phenol oxide, this is phenol oxide, this negative charge due to resonance is dispersed over the benzene entire carbon atoms of the benzene ring. That means more the dispersion of the charge, more will be its stability, and more the stability, more will be its acidic strength. Please remember that. And here no such effect takes place. Moreover, here you have already had C2H5 O minus. Now C2H5 is known to show plus I effect. That means more electron density over oxygen will be increased, and it makes it very unstable. Now based on the stability of conjugate base, as I told you, the acidic strength of phenol will be more than that of what? Ethyl alcohol, because of resonance takes place in the phenol oxide ion, which is the conjugate base of phenol, and it makes it very stable. And if this is very stable, the forward reaction takes place and more amount of H plus ions will be generated, and you can link the amount of the concentration of H plus ion to acidic strength. More the concentration of H plus ion, more will be its acidic strength. Okay? So the second point, relative strength of bases. Now let's discuss about relative strength of bases. This is number 2 now. Relative strength of bases. Now let's compare between CS2, CS3, NS2, and say this is aniline, this is aromatic ring. So aromatic amine, this is aromatic amine, and since you have this carbon chain over here, no ring form, this is aliphatic. We call it as aliphatic amine. Now out of these two, which one will be having more basic strength? Now basic strength, as I told you, this depends upon how easily it can donate its lone pair of electron. Nitrogen has lone pair of electron. Here also nitrogen has lone pair of electron. Now in case of aliphatic amine, this lone pair of nitrogen. So in this case, in case of aliphatic amine, you have a lone pair of electron, and this CS3 group moreover shows plus I effect. Now plus I effect, due to the plus I effect of CS3 group, the electron density over nitrogen will be enhanced. Therefore, now these lone pair are always ready to be donated. Whereas in case of aromatic amines, this lone pair over nitrogen takes parts in resonance, and they are not available over nitrogen. And because of this aliphatic amines basic strength is always greater than that of what? Aromatic amines. Why? So here you have to remember, for basic strength, more easily the electron can be donated, that will be more basic. But in case of this aromatic amines, the lone pair over nitrogen is not available. Why? Because this takes part in resonance in the benzene ring and is distributed over all the carbon atoms. Whereas in case of aliphatic amine, the lone pair is available. It's not taking part in any sort of such effects. Moreover, CS3 shows plus I effect and increases the electron density over nitrogen. Hence, these electrons are easily available for them to be donated. Therefore, the basic strength of aliphatic amines are always greater than that of what? Aromatic amine. Now, let's discuss about the third application, that is relative reactivity of alkyl halides and aryl halides. So third application is relative reactivity of alkyl halides and aryl halides. So alkyl halides means you have alkyl group, say CH3, halide, let's say you have BR, and aryl means the benzene group. Okay, aryl means the aromatic benzene group. So here you have BR. Now we are going to compare about their reactivity. So for that we have to see what here single bond is present, and moreover this BR and this BR, the reactivity, okay, of halogen depends upon how easily this BR can be removed from either aliphatic amine or aryl, not amine. Here we are discussing about halides. So this is alkyl halide. How easily this bond can be dissociated? More easily this bond can be dissociated, that will be more reactive. Please remember this. Now, in this case, we have a single bond, and BR, you know, it's delta negative, and this is delta positive. Therefore, the electrons are shifted somewhere near to the bromine. Moreover, CH3 shows plus ion. Because of this, these electrons are more towards bromine than towards carbon. That means it is already polar. Now, let's come to this aryl halide. In case of aryl halide, what happens is this bond, which you see as single bond, is not a single bond. Okay, why? Because you know bromine has lone pair of electron. Now this lone pair takes part in resonance. So whenever it takes part in resonance, now this bond between this carbon atom and this bromine is no more single bond. It will have a double bond character. Please remember, it will have a double bond character. Here, this is having double bond. Now, because of what? Resonance taking part in this particular aryl halide. So, from your common sense, you can say it. Is it easy to break the single bond, or is it easy to break the double bond? So, obviously, it's always easy to break the single bond. And remember what did I say at the beginning? I said to you, more easily this bond between halogen and the carbon breaks, that will be more reactive. So by now you must have understood which one is more reactive. Obviously the alkyl halide, this is alkyl halide, is more reactive. Why? Because it has a single bond, and that too is a polar bond. But in case of this, here you have some delta negative charge. Now here, not delta, this is negative charge. Okay? So here, because of resonance of the lone pair of bromine inside the benzene ring, this bond is no more a single bond, double bond, and it is very difficult to break the double bond. Hence, its reactivity is less. What's reactivity is less? Aryl halides reactivity is less compared to the alkyl halide. So these were the three main important applications of resonance. Now, on your book, on page number 12.67, there's a difference between tautomerism and resonance. Please go through the differences. The next topic is hyperconjugation. The next topic is what? Hyperconjugation. We have hyperconjugation. JU, hyperconjugation. So hyperconjugation is also known as no bond resonance. Now Now for this hyperconjugation to take place, there has to be presence of this double bond, and there has to be alpha hydrogen. So in compounds such as this one, you have double bond over here, so CH2 and H. Now here you have double bond, and here you have Z. This as a whole contains this carbon, and carbon contains double bond. Now the carbon which is attached to this carbon is alpha carbon, this alpha carbon, and the hydrogens which are attached to alpha carbon are what? Alpha hydrogens. These are what? Alpha hydrogens. So in such cases, what will happen is this sigma bond between hydrogen and carbon, alpha carbon and alpha hydrogen, it takes part in resonance. This bond breaks over here, and this double bond will be shifted over this carbon atom. Now, what will you get? You get hydrogen, carbon, hydrogen, and here you have a double bond now because this both electrons it has come between this carbon and carbon. Now here you have CH, and here you have a single bond CH2, and here you have a negative charge. And that H will be staying as H plus over the carbon. Now such effects where sigma bond takes part in conjugation with what? The pi bond. Now such effect is known as what? Hyperconjugating. Hyperconjugation has said to be taken place in such cases. Okay, and this is also called as no bond resonance, and it has another name also, Baker-Nathan effect. Now the definition is hyperconjugation is an interaction between p orbital and adjacent CH sigma bond. So here CH sigma bond is there, and here there is a p orbital. Now it is also defined as the delocalization involving sigma bond. You can see that the sigma bond, single bond is there, sigma bond. Now this is taking part in what? Resonance with the pi bond here, and this effect is known as what? Hyperconjugation. Now you have to remember alpha carbons. How many hyperconjugated structure will a compound have? It depends upon the number of alpha hydrogens. Okay, so here you have 3 alpha hydrogens. This particular compound will have 3 hyperconjugated structures. And you have to remember one more thing. More the number of hyperconjugating structure, more will be its stability. So it's very simple. It's very simple. The number of hyperconjugated structure depends upon the number of hydrogen, alpha hydrogen. Please remember alpha hydrogen. You need to identify alpha hydrogen first in the compound. So alpha hydrogen, hyperconjugated structure depends on the number of this alpha hydrogen, and more the number of hyperconjugated structure, more will be the stability. In a sense, it means more the number of alpha hydrogen, more will be the stability of that particular compound. So you have been given this its stability order. Okay, always the tertiary is always tertiary means what? You have CS3, 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 and here you have a double bond. Okay, so these are all alpha carbons, 3 alpha hydrogen, 3. That means it will have 9 structure. Therefore, this will be always what? More stable compared to secondary. Secondary will have 6 alpha hydrogens, and then comes first degree. First degree will have 3 alpha hydrogen. Okay, and respectively that many hyperconjugated structure. So the significance of hyperconjugation effect is given. Okay, now here stability of alkyl. They have compared between different structures. So let's discuss this part. So significance means you can say application. Significance of hyperconjugation. So they have given you CS2, double bond CS2, then they have given you CS3, CH double bond CH2, number 2 structure. Number 3, they have given you cis butene. Cis means the more priority group lying on the same side. Another one is trans. So let's take this for examples. And here you have hydrogen, here you have hydrogen. Now, out of this 4, which one is more stable? Please tell me. So here you don't have any alpha hydrogen, therefore it doesn't have any hyperconjugated structure. Here this has 3 alpha hydrogens. That means it will be having how many hyperconjugated structure? 3. This has, see, these are alpha carbons and these are alpha hydrogens. This has 6 alpha hydrogens and this also has 6 alpha hydrogens. Now obviously this has 0 alpha hydrogen. Therefore there is no question of hyperconjugated structure. So from the hyperconjugated perspective, we can say that this is a least stable. After that comes this, because it has only 3 alpha hydrogens. But here this compound and this compound has 6 alpha hydrogens and 6 alpha hydrogens. And you tell me now, in such cases, the stability will be decided by what? The position of the bulkier group. You can see that this CH3 is bulky group and this CH3 is also bulky group. Since they are lying on the same side, now they will be interacting with each other. Whenever there is interaction between these bulky groups, they tend to be less stable. Therefore, you have to always remember this cis form is always less stable compared to the trans form. This trans. In trans, you have molecular group lying far apart from each other. Therefore, there is no question for this steric hindrance. Okay. So the most stable one will be your trans form. Then comes your cis form of butene. Then this, and the last one is S. So based on hyperconjugation also, we can discuss about the stability of alkyls. And so there are a few other examples. Okay, directive influence is given, and let me tell you, whenever this CH3 group is attached to the benzene ring, they will always be ortho-para directing groups. Now say this CH3 group is attached to the benzene ring. Whenever the CH3 group is attached to the benzene ring, then what will happen is this. So let me write it separately. Carbon is in, we have hydrogen and hydrogen. Now this takes part in resonance with this. Because of this, it will have negative charge over here. So finally, because of this hyperconjugation, you will be having negative charge over here, negative charge here, and negative charge here. Okay? Because of what? This hyperconjugated effect. And whenever you have some electrophile, say electrophile means electron level, then they will either come to ortho position or to the para position. So this is ortho position, this is meta position, and this is the para position. So you can see, because of hyperconjugated effect, the negative charge comes at ortho position and para position. Obviously, common sense, if there is some electron loving group, it has to come to that position where there is electron. Therefore, this CH3 group will, whenever it shows this hyperconjugation, it will be acting as ortho and para directing group. Ortho-para directing group means it will force the incoming electrophile to come to either ortho position or to the para position, but not to the meta position. Okay, so with this we come to the end of the application of hyperconjugation. Please keep revising. These 4 effects are very important, and once you can see in a compound which effect is prevailing, then you can decide how the reaction will proceed. Please, this part is very important. practice it properly.